Okay, I'm going to go through completing the square and how beneficial it is to spot completing the square. So the first thing, as I said to you, is you have to get used to quickly expanding that. So it would be a square of that, a square of that, and then this times that times 2. And you can also learn it for cubes and to the 4 and to the 5, and it's something called I think it's called Pascal's triangle. And you can learn whatever coefficients go with various squares, cubes, and to the power 4. But right now you got to learn to the square right now, and you got to learn very quickly. It's the square of the first one, it's the square of the last one, which always ends up being positive because squares are always positive, and 2 times the middle terms times each other. So that is the expansion of that. So that is the goal of converting. If this is the standard form of the parabola, that's the standard form. This is the vertex form. And from this one up above, you can see that there's no y value here. So the vertex of this top one is minus 3 comma 0. However, you're not always going to have this perfect square situation to convert back to the vertex form, and that's why we're learning this. You can, however, construct your perfect square out of any standard form parabola. So let's say you have, let's just start with a simple one. Let's say you have x squared as a standard form plus 8x plus 22. So this is clearly not a perfect square. However, if you look at this component right here, you can see that it has aspects of a perfect square. What perfect square would happen to create this part of it? Well, as I remember, the middle term is created by 2 times the terms multiplied each other. So what gets multiplied by 2 to get 8x? Well, it's 4x, which means the first term would be x, and the second term would be 4. So this here, x plus 4 squared, would create that middle part right there. Well, let's test that out. Okay, go all the way back. So let's see if x plus 4 expanded creates this part right here. Sure enough, you're going to discover it does every time. To figure out what the perfect square is, you would just divide this part by 2. And that's simplified for now, but we'll see. So when I expand it, sure enough I get that, but I also get this extra number right here. So yes, I've successfully created the perfect square I want here, but I all of a sudden have this 16 that I didn't necessarily need. Now fortunately we have 22, and 22 certainly can be broken down into 16. You can break down any number in a math equation any way you like, so long as you follow the rules of math, and 22 can be broken down as that. So this is the same equation. Plus 16 plus 6 is the same as plus 22. All of a sudden, if I take this component of it right here in green, I have my perfect square. And now I can replace that part of it, the part in green, with x plus 4 squared. And then way over here I have a plus 6. And sure enough, as you've just seen down below, if I expand that part of it, I do indeed get that part of the perfect square right here. And I have a little 6 left over because of that 22. So that means that x squared plus 8x plus 22 is the same as x plus 4 squared plus 6. And we can see that we've converted this nice standard parabola right here into a vertex format. And the vertex there is minus 4 comma 6. So learn your vertex format first of all. If you don't know how to find the vertex from that, it's always this number and that number, but it's the x is always the reverse sign. And you also have to be aware that your x cannot have anything in front of it. It's always 1x. We'll get to that in a second. But look at that. I've converted this to vertex form using a perfect square. Let's go back a little bit Let's go back a little bit. There's another thing I want to touch on, which is called partial completing the square, which is incredibly useful. So all of a sudden, I know right away that I'm aiming for x plus 4 as my perfect square. And you might say, well, now I got to figure out what the extra numbers that are created. But right away, I can say x plus 4 will always create that 8x situation. That's what I'm getting at. But notice that right there, I now have the x value of my vertex. That's my x value of my vertex. I could go back and plug it into the original equation. This is called partially completing the square. And when I put minus 4 into x squared, I get 16. When I put minus 4 into 8 times plus 8x, I get minus 32x. Oh, it's minus 32. And then I've got this plus 16 here. And sure enough, oh, wait, got to remember it's plus 22 here. Plus 22. And remember it's plus 16 plus 22. I shouldn't have written it like this. But plus 22. So when these cancel, I get minus 16 plus 22, I get plus 4. All of a sudden, by using the plus 6. All of a sudden, by using the perfect square, I have determined, sure enough, by doing partially completed square, I've determined that this is indeed the vertex format of plus 6. I didn't have to fiddle with my 22. I could just figure out my minus 4, plug it in here, and I would immediately get my y value for my vertex. Then I could rewrite my vertex formula. Let's try both methods a few times. So you can write down any parabola you want. It doesn't matter. It can be minus. You might say, I notice you're making let's just stick with a normal one. I notice you're writing down even numbers in the middle, and it doesn't matter. So I'm just going to put that. So there's our parabola, and I've got to remember to put a square here. And right away, you just start by saying, what would create that part of the perfect square? And right away, I know it's going to be x, right, minus 7 squared. How did I know that? I took this here and divided it by 2. And I already know it's the first term times the second term, or if I want the first term times the second term times 2. So to reverse that, I just divide the middle term by 2 to figure out that this is indeed my perfect square. If you're not sure, you can always expand this. You can always expand this to make sure. If I expand that, I get x squared minus 7x minus 7x plus 49. That's the number I don't want, but I'm just looking at this part of it right now. And sure enough, I get, look at that, x squared minus 14x. That matches the square. Now I have two opportunities right here. Right now I know immediately my x value of my vertex is going to be plus 7. I can do partially completed square and just put plus 7 into this and figure out my y value for my vertex. Or I can use this method. So as we've discovered, a plus 49 is created that we didn't necessarily have before. So I need to borrow 49 from this 103. And there's other ways better ways of instead of borrowing the 103, I'm just using it to explain. So if I break down 103 into something with 49, I get plus 49 and plus 54. So I can now loan that 49 from my 103 to get my perfect square here. So I can replace the formula with x minus 7 squared. And this plus 54 is left over. So now I know my vertex, that's fully completing the square. My vertex is plus 7, comma 54. Let's skip that 54 part. We're going to go back. And we're going to take, before we knew it was 54, we're going to take this 7, and we're going to put it into the equation up here. 7 squared, 49, minus 14 times 7. Let's do that quickly. It's 98 minus 98, plus 103. Also notice that there's a pattern going on here. But anyway, plus 903. So when I subtract these, I get minus 49. There's the pattern. And plus 103. And I'm left with 54. So by partially completing the square, I could go back, find my y value of my vertex, and just tag it on there. Now I have a vertex format for completing the square. And it's very, very handy. I like partially completing the square. I find it faster because sometimes these numbers get very complicated. Okay, let's take a very complicated. It's fine when I'm starting with just 1x squared, but what happens when I start with like 4x squared? And I'm going to start with a simple one so that you can see. And it doesn't matter what this number is. I can make it anything. I can make it 237 if I want. I can make it 2. Let's make it a tough one, 2. Okay, the secret here is isolating this and factoring out whatever's in front of the x squared. So I'm going to factor out 4 from both these terms. Factoring out just means I'm dividing both these terms by the number I'm factoring out and putting those in brackets. So what's 4x squared divided by 4? 4? It's x squared. That's what we're aiming for. Plus 16 divided by 4, it's plus 4. So right there, by factoring out a 4, I have discovered what, plus 16x, I've discovered the first part of the square that I need to work with. I'm going to forget all about this 2. This 2 I call Larry, and I'm just going to push him off to the side and forget about Larry. We need to figure out what the perfect square of this is. So far all our numbers are intact. The perfect square of this is half of that value, so it's x plus 2 squared. What gets created when I expand that? By the way, it's a good idea to put all of this right now in green square brackets, and you'll see why in a second. So what's the expansion of x plus 2 squared? It's x squared plus 2x, which is plus 4x, plus 4. So in blue, that's the number I've suddenly created that isn't part. I got this in there already, so it exists, but this does not exist in there. So that means I'm creating a plus 4. So to turn this into that, I would end up with this, so I have to get rid of the 4 I created. I might have lost you there. I'm going to replace this whole thing with this. But if I do that, sure enough, I get exactly what's already there, but I'm creating a plus 4 that wasn't there, which means I now must subtract that 4 to balance this out. So I'm going to rewrite it instead of just throwing the minus 4 in there. I'm going to rewrite it as 4 x plus 2 squared minus 4, and remember, we're going to keep it all in the green brackets. And don't forget about Larry. You can just grab Larry and move him down. All right, does that make sense? Let's find out. If I was to expand this, I'm trying to get back to this. If I was to expand that, I'd get x squared plus 4x plus 4 minus 4, right? Oh yeah, you sort of got to keep that in brackets too. These would cancel out. I'd get x squared plus 4x times 4, which is exactly what I have up here. So you can see by subtracting the 4, I've balanced my equation. I'm creating this. So essentially, when you're turning this into the completed squared, you have to subtract the number that you accidentally create in the completed square. Now there's a second problem, and that is that this whole thing is being multiplied by 4. So if I'm going to create a nice balanced y number outside of these green brackets, I'll just keep this here, but this 4 will distribute to the minus 4 to kick it out of the brackets. So what's 4 times minus 4? It is minus 16, and then I still have Larry, plus 2. What's minus 16 plus 2? It's minus 14. So right there, I've created the vertex format. I'm left with 4, so it's an upward-facing parabola, x plus 2 squared minus 14. To test this out, You can take the original parabola and put it into your decimals. And then you can take your vertex formula and put it into your decimals. What was it that I had? I had plus 2 squared. And it was what? Plus 16? Minus 16, right? Minus 14. And they should match up perfectly. And sure enough, they do. So if I turn the blue off, on and off, it's the same parabola. And even just looking at the standard format, which is in red here, you can see that, yeah, if I had the graphing tool, I can see the parabola, the vertex right away. But my point is I'm showing you that by completing the square, I can reconstruct the standard form parabola into vertex format. Obviously, going from vertex format to standard is very easy. You just expand this, multiply by 4, subtract, and then just subtract 14 and figure out what your x squared, your x value, and your y-intercept is. Notice that this gives you the y-intercept right away. So up here you can note that if we go through that. Let's go back to what we did and notice how much longer that was, right? And let's just reach this stage here where I'm going to rewrite it. Rewrite it as 4x squared plus 16x plus 2. Okay. And I'm going to push that 2 aside. And I'm just going to factor out the 4 from the middle. So I get 4x squared plus 4x. And we're going to do a partial completion this time. And then there's plus 2 over there. So all I did was factor out a 4 from this part to create that. And I can see right away that my perfect square would be x plus 2. Now I'm going to stop x plus 2 because I have my 4 here, and I know it's going to be squared. I just don't know what number it's going to be. I mean, I know now it's going to be minus 14. But instead of doing that complicated multiplying by 4 and getting the number outside the brackets thing, I know my vertex is minus 2. So I'm going to go back here and plug in minus 2 to figure out my y value that I would just tag up on here, my y value of my vertex. It could be a lot easier. So minus 2 squared is 4 times 4 is 16. Minus 2 times plus 16 is minus 32. There's that pattern again. So the number I ended up with is minus 16, which looks familiar. Plus 2, because I bring the 2 down, add it, and I get minus 14. So sure enough, it was a little bit faster doing it this way, because now I can just rewrite my vertex formula as y. And yeah, I'm not doing it in function format by the way. And now I know my y value is going to be minus 14 by just taking the partially completed minus 2, putting it back out into here, and it spits out my y value of minus 14. Now I can just throw that on the end of my vertex formula. So it's actually, I like doing the partially completed square because sometimes you can make a lot of number mistakes getting the number that you created by the perfect square out of the brackets. This, I find, can be a lot cleaner. It's not as clean when you use fractions and things, but even then, fractions, it still works. Just your calculator won't spit out fractions. So this is completing the square, and it comes into the 3 formats of the vertex that you need to know. Standard, the only information you get from standard is the y-intercept. Vertex tells you a lot more. Oh, and that it's facing up or down. But they all tell you that. This one you get facing up or down, and the vertex. And the other one's called factored format or intercept format. And it looks like x for x minus something. Would be, I think they call it a, x minus b, x minus d. And what those tell you is where it intercepts the y-axis. So if you look here, you'll see our x-axis intercept, our x-intercept is minus 3 point. So it's not clean. It's never that clean when the vertex is clean. But you could probably guesstimate and do x as one of them, because, oh, no, it doesn't go through 0. It's x, so it'll be x plus 0.129, and it won't be accurate because Desmos rounds up. And x plus 3.871. And sure enough, there we go. My green one now matches my blue one, which also now matches my red one. So I did that from the graph. I created the factored format. You can indeed, and you will have to learn how to do factored formatting. And when it's not clean like this, you have to use something called the quadratic formula, but we're going to get to that. I want to go back a little bit and discuss something interesting about the standard format. You can actually find the x value of the vertex from the standard format, and I believe if you Google it, finding vertex from standard form, because yeah, there'll be videos explaining it too, but there's always going to be an image. And yeah, it's minus b divided by 2a. So minus b divided by 2a. So let's say you have a standard form, and I'll just steal it from Desmos here. Minus b divided by 2a. So let's say you have these three here, and you don't want to go through completing the square. So it goes ax squared plus bx plus c is the standard form that you'd use for the quadratic formula as well. But the vertex is right there, so it's minus b. So what's our b? Plus 16. So we opposite sign it. Minus doesn't mean always make it minus, it just means change the sign. So you get minus 16 divided by 2a. What's our 2a? 4 is a, so 2a is this. And sure enough, it spits out my y value, or my x value rather, of the vertex. So remember that. It's minus b, so the opposite sign of b divided by 2a. This makes more sense when you get more practice, because actually by completing the square, that's exactly what we're doing. We're looking at what's in front of the x when we factored out that 4. We're taking the opposite of this, which is what we do for all vertexes. So it actually makes a lot of sense. Why the 2? Because remember, when you complete the square, you're multiplying the two terms by 2. Because when they expanded, there was 2 of them. So you get used to the connections of these numbers. Anyway, that's a good thing to keep in mind, because once you get the x value, you can then plug it in. So if you're stuck and don't want to complete the square, just remember that within the standard form, the x value of the vertex is minus b over 2a. And then you get it. And actually, there's a better way of doing like this factored form. We obviously didn't have clean factors. There is a better way than the quadratic function, which is b squared. I think it's plus or minus. Oh, yeah, it's minus b plus or minus the square of b minus 4ac over 2a. There's a connection to this formula to exactly what we do when we factor something. And I'm going to give you the alternative of the quadratic function. I might as well get a clean one up. Quadratic function is used when you cannot find the factors of something. Quadratic equation, I think it's called. Formula. Yeah. Did I get it right? Yeah, I did. So there it is right there. So when you cannot factor something, you you have to put it in the standard form. It only works in the standard form, which in this case is right here. Our A is equal to 4 here. Our B is equal to 16. And our C is equal to 2. You can forget all the x's and everything. And then you just take these values and you plug them in to the quadratic formula. C is only used once, and B is used multiple times. However, this plus or minus must be used once where you add the square root, which is called the discriminant, and subtract the discriminant to come up with the two possible roots. The other thing you should realize, you can develop a formula like this in your calculator or your Excel sheet, so you don't have to do it over and over again, but the discriminant becomes very important. If the discriminant, if this whole thing in here comes out to 0, then the vertex of the parabola touches the x-axis. If the whole thing comes out to positive, then there's indeed two possible factors. And if the thing comes out as negative, there are no possible factors. You might say, how can there be no possible factors? Well, some parabolas never cross the x-axis. This parabola here never crosses the x-axis. Therefore, it would never have factors. So you would get a negative result from that. Same with a downward-facing parabola below the x-axis, never crosses the x-axis. So in the b squared minus 4ac, the ac often is so much bigger that it becomes a negative, and you can't square root a negative. So there's no factors for those. So learning the discriminant can save you time as well, because if you calculate the discriminant and come out with a negative, there's no point in doing the rest of the quadratic formula. Your function is above or below the x-axis. Hope that was helpful. There's lots of videos on completing the square. I actually think partially completing the square is very useful. So is the minus b over 2a formula to find the x value of the vertex in case you want to verify it to make sure you're completing the square correctly. But you also will learn another trick that I'll show you next time that's incredibly useful. It's like doing the quadratic function, but by hand, and it's actually faster and makes more sense. And I'll try to teach you that next time. Hopefully that helps somebody.